Now I would like to discuss the validity of the classical explanation of the behavior of an ideal gas. If you remember, we talked about some criteria for a classical discussion. One was that the thermal energy kT must be much greater than the separation between energy levels in the quantum description. And two, the minimum distance of interest should be much greater than the de Broglie wavelength, that is basically h bar divided by the linear momentum of the particles. So we should take a look at the typical momentum of a molecule in this classical gas. So the typical momentum that we can consider would be the momentum corresponding to the most likely situation. So typical momentum of a molecule in this ideal gas at thermal equilibrium is going to be equal to the mass of one molecule times the most probable speed of the molecule. And since we have found out in our classical discussion that this most probable speed of a molecule is square root 2 kT over m, the typical momentum is going to be square root 2m kT. Now, we can calculate the corresponding de Broglie wavelength. The corresponding, because that is the characteristic length scale that is of interest for us in order to decide if we want to use classical or quantum description. So the de Broglie wavelength, the reduced de Broglie wavelength, lambda bar d, is the reduced Planck's constant divided by the typical momentum of the molecule. So this is going to be h bar divided by square root 2m kT. Now, the criterion that we had was for quantum effects to be negligible, we need to have the separation between the molecules to be much greater than the de Broglie wavelength. So that means the gas should be sufficiently dilute. So I call the separation between gas molecules as 0. This should be much greater than the reduced de Broglie wavelength, or I can say the ratio reduced de Broglie wavelength divided by the separation between the gas molecules should be much less than 1. Now I need to have a method to estimate the separation between the gas molecules. So in solids we have these crystals that consists of face-centered cubic, simple cubic structures, etc. So in order to estimate S0, I'm going to use a simple cubic model. This is just to give me an idea what S0 should be. So in the simple cubic structure, we have atoms or molecules in this case residing at the corners of the cube. So maybe I should make this more like a cube. And if you put these atoms at the corners, we find that inside one cube we're going to have a total of one atom or one molecule in this case, because there is 1/8 of an atom at each corner, because each atom at these corners will be shared by 8 cubes. So this is going to continue like this, it will continue like that, etc. So it will be shared by 8 cubes. So there is 1/8 times 8, 1 molecule per cell, or per cube in this case. And the distance between the molecules I have called S0. Then I have S0 cube is the volume occupied by one molecule, and the total volume occupied by capital N molecules, n times S0 cube, will be equal to V total volume. So I will find that S0 should be V divided by N to the power 1/3. So this is actually the number density to -1, 1/n to the power 1/3. So N number density is capital N divided by V, and this is N to the power -1/3. So for the classical discussion to hold, the ratio of the reduced de Broglie wavelength to S0 should be h bar divided by square root 2 mkt, that is the de Broglie wavelength, multiplied by m, because it's 1/S0, n to the plus 1/3. And this ratio should be much less than 1. So that is the criterion for the classical discussion to hold. And basically it is telling us that as long as this n is sufficiently small, so n must be sufficiently small, so the gas should be dilute, or dilute enough, and the temperature should be sufficiently high. T must be sufficiently high for the classical approximation to be valid. So that is the criterion, and it basically boils down to the same thing we said earlier. The thermal energy should be much greater than the separation between energy levels, and the minimum distance of interest should be much greater than the de Broglie wavelength. So that's what we observe for the criterion for this approximation to hold. Now let's make some numerical estimates based on this result. So I'm going to demonstrate this for a helium gas. So a numerical estimate. Let's consider a helium-4 gas. Okay, the gas is at room temperature, and the pressure is 1 atmosphere, 760 millimeter mercury, or 1 atmosphere pressure. So in SI units, that means the mean pressure that this gas exerts is 1.01 10 to 5 pascals. So pascals is force per area, Newton divided by meter square. And room temperature, KT, the thermal energy, we can estimate it to be 1/40 electron volts, which is 1/40 multiplied by 1.6 10 to minus 19 coulombs. So that is 4 times 10 to minus 21 joules of thermal energy. And what is the mass of one helium atom? the atomic weight is 4, so divided by Avogadro's number, 6.02 10 to 23, gives me 6.6 times 10 to minus 24 grams, or it is 6.6 10 to minus 27 kilograms. Now, we can calculate the N value, the number density, using ideal gas law. P bar V is equal to NKT, or I can say that P bar is equal to NKT. So the number density N will be P bar divided by KT. And P bar is 1 times 10 to 5 pascals. KT is 4 times 10 to minus 21 joules. So the answer is 2.5 times 10 to 25 molecules per meter cube. Then I can calculate the reduced de Broglie wavelength. So this one. The de Broglie wavelength, lambda de Broglie, will be h bar divided by square root 2mkt for the most probable momentum. The Planck constant h is 6.62 10 to minus 34 joule seconds, divided by 2 pi is the reduced Planck's constant, divided by square root 2 mass of one helium atom, 6.6 10 to minus 27 kilograms, multiplied by thermal energy 4 times 10 to minus 21 joules, and this gives us, for the de Broglie wavelength, approximately 0.14 angstroms, and 1 angstrom is 10 to minus 10 meters. And for S0, the average separation between the molecules, this is estimated to be n to the power minus 1 over 3 using our simple cubic model. So 2.5 times 10 to 25 to the power minus 1 over 3 gives us, for the average separation between molecules, 33 angstroms. So if we see that S0 equals 33 angstroms is much greater than the de Broglie wavelength, which is equal to 0.14 angstroms. So the conclusion is that classical approximation at room temperature is valid. Now let's do the same exercise for a different material. So this was for helium gas. Now I want to do the same exercise for a copper metal. So let's consider copper metal conduction electrons. So this is going to be the second system I will look at. Okay, so what is the mass of an electron? The mass of an electron is roughly 10 to minus 30 kilograms. Then I can calculate the reduced de Broglie wavelength. The de Broglie wavelength is h bar divided by P0, and you can see that since the de Broglie wavelength is proportional to square root of m, square root 2m kT, so this is at room temperature as well, and the same atmospheric pressure. H bar value and mass kT values are the same with this previous example. So I see that the reduced de Broglie wavelength is varying as 1 over square root m. So the mass of one helium atom was 6.6 10 to minus 27 kilograms. Now the mass of one electron here is 10 to minus 30 kilograms. So in comparison to helium gas, I find that the ratio of the masses, mass of the helium atom divided by mass of an electron, is 6.6 times 10 to minus 27 kilograms divided by 10 to minus 30 kilograms. So the ratio is 6,600. So an electron is 6,600 times less heavy than a helium atom. All right. Then, since the de Broglie wavelength is proportional to 1 over square root of m, the de Broglie wavelength for the electron will be 0.14 angstroms times square root 6,600. It's roughly 10 angstroms. Now let's say that we have one conduction electron per atom, and S0 in that case, the separation between the average separation between the electrons will be equal to the lattice spacing, again assuming that I have one atom per cell, so that S0 is a good estimate for the separation between electrons. So this is again a model. We're assuming a simple cubic model where we have the copper atoms at the corners and the number of conduction electrons provided by one atom is 1. So electrons, or electron gas, if you wish, cannot be discussed classically. Why? Because S0, the separation between the electrons, average separation, is less than the reduced wavelength. So we need to use needs quantum treatment. All right. So we gave two examples, one an ideal gas of helium at room temperature, and two the conduction electron gas inside a copper metal at room temperature, and we see that for one system it is possible to discuss it classically. For the other one we have to resort to quantum mechanics because simply because the mass of an electron is much less than the mass of a helium atom. That results in an increase in the de Broglie wavelength. All right, so we talked about the validity of the classical discussion of a gas, and we recall that we need to have a large thermal energy and also a large separation between the gas molecules for this to hold. And looking at our discussion using Maxwell distributions, we have found the most probable speed of a molecule is square root 2 kT over m. So the most probable momentum is square root 2m kT, and we can calculate the de Broglie wavelength h bar divided by p0, h bar divided by square root 2m kT. And the separation between the molecules we can estimate using this model of a simple cubic structure where we have all the molecules residing at the corners of the cube, and S0 is the average separation between the molecules. And in this model we have 1/8 of an atom or molecule shared by each cell. Therefore we would have one molecule per cube. The cube of the volume, the volume of the cube with S0 cube, which is the volume occupied by one molecule. Total volume occupied by the gas is number of molecules n, capital N, multiplied by the volume occupied by one molecule. So that tells us that S0 is number density n to the power minus 1/3, and the ratio lambda bar d divided by S0 should be much less than 1, is telling us the gas should be sufficiently dilute, the temperature should be sufficiently high for the classical approximation to hold. If we give some numbers for the helium gas, we have found that the Broglie wavelength is 0.14 angstroms, and the average separation is 33 angstroms in our model. Average separation is much greater than the de Broglie wavelength, therefore classical approximation at room temperature holds for the helium gas. In the case of an electron, because its mass is much smaller than that of the helium gas molecule or atom, then we have a reduced de Broglie wavelength much higher, about 10 angstroms, and that compared to the lattice spacing in the copper crystal, where we assume that we have one conduction electron provided by one atom in a simple cubic structure also, the S0 value is less than lambda bar d, which means that electron gas requires quantum treatment.